Hi everyone. Today I want to talk about advanced trigonometric identities, specifically two in nature. The first one, the Pythagorean identities. These are super important when it comes to verifying, completing, even when we get to the solving portion of trigonometric identities, and then solving equations after that. So there are three big ones, right? And when we talk about the Pythagorean identities, we obviously mean the Pythagorean theorem. Now remember, we've done practice problems on this channel multiple times about finding identities or values of one of the six trigonometric values if you're given one of the one. So the biggest one obviously is the first one. Sine squared of theta, or x, plus sine squared of theta, or x, equals 1. Now we know that because if I square any sine value and I add it to a squared cosine value, I should equal 1, because 1 represents the radius of any line or any radius from the unit circle, or on the unit circle, or off the unit circle. Not that last one. That doesn't make sense. The second one, tan squared of theta plus 1 is going to equal secant squared of theta. And then finally, it could go either way. I don't really know why I did it that way. But 1 plus cotangent of theta squared of theta equals cosecant squared of theta. And then obviously vice versa, I could add it or one way or the other. Now, when we talk about why these work, we really mean radian measurement, because if you use degree measurement, it's not going to work out the way you think it's going to. So when we talk about radians, that's what we're looking for. Case in point, let's take the first one and just kind of dissect it a little bit. Well, what if I said theta was the measurement of pi over 4? Well, we know that pi over 4 is an easy one because it's root 2 over 2, comma, root 2 over 2. Well, if I were to substitute root 2 over 2 in for both of these values and square them, root 2 over 2 squared is 2 over 4, or 1/2. And 1/2 plus 1/2 is 1. So that's just a basic identity to work it out. You could use this with any ordered pair on the unit circle and it'll still work. Now, the other set of identities we'll talk about today are even and odd, not even minus odd. It's just even or odd. Now, these are really simple actually, and you could just use theta as well. But anytime we have a negative x value or a negative theta value for sine, we could just simply take that negative out and put it in the front and makes the entire sine function or sine identity negative. Same with cosine, same with tangent. Obviously cosecant and secant and cotangent would be the same as well. Now, is this one as important as the Pythagoreans? No, not at all. But when we talk about advanced trig identities, before we get into the heavy duty half angle, double angle stuff, we're gonna use these two. So let's work out some practice problems. Number one, we want to verify that cosecant squared of x minus cosecant squared of x times cosine squared of x equals 1. Now, remember here, PEMDAS is super important. I'm not allowed to move anything really from one side to the other. And remember, we also talk about things that are LHS as left-hand side and RHS as right-hand side. Typically, we do not want to do anything to the right-hand side. We want to leave the right-hand side as it is. When we think of these identities and verification or even completing them, we need to think of it like a puzzle. And you know, when you do a puzzle, you throw the pieces all over the place and you use the box or the picture on the box as the end result, as what you're trying to get to. So you can like put your reds, your greens, your blues to one side, obviously get the corner pieces and all the edge pieces, but you're using that box as kind of the goal, right? So when we do trigonometric identities, whether they're basic or advanced, we really want to use that one or that thing on the right-hand side as our goal. We want to get to that because that's what the end result should be. Now, when we get to that verification, it'll be great because you know that you have LHS and RHS equal to each other. Let's go ahead for it. Now, with the Pythagorean identity, it's not super clear right yet, but we know that cosecant is 1 over sine. So let's go ahead and do that. We know that cosecant squared is just going to be 1 over sine squared x, or theta. It doesn't matter right now. And we know that cosecant is also, again, 1 over sine squared x. Now, that second 1 over sine squared x is also being multiplied times cosine squared of x. And then obviously we're going to equal that to 1. So now that we have re-imaged, so to speak, our cosecants into 1 over sine squared, let's go ahead and combine like terms as we know so. Well, first we have the parentheses, or first we have the multiplication here. So I have 1 over sine squared x minus cosine squared of x over sine squared of x. And that's supposed to equal 1. Well, now we have a fraction with a common denominator. Both denominators of these fractions have sine squared x. Well, let's just go ahead and put all this together. So now I'm going to have 1 minus cosine squared of x over the consistent denominator of sine squared of x, and that's going to equal 1. So I really didn't do anything here except for combine like terms. Now, I'm going to have to do a little bit of finagling. There is a denominator that I need to get rid of because I don't like levels. Let's multiply by sine squared x on both sides of the equal sign because that's going to cancel out the 1. It's going to move this sign over and go from there. So then I have 1 minus cosine squared of x equals sine squared of x. Now, technically speaking, that is the identity, and that's fine because back to our Pythagorean identity of sine squared theta plus cosine squared theta equals 1, this says the same exact thing. Now, if you want to get really fancy about it, let's go ahead and add cosine squared of x to both sides. Oh, you can't see that. That sucks. Okay, so what I did was I added cosine squared of x to both sides. Now I have 1 equals sine squared of x or theta plus cosine squared of x or theta, which is the identity, and check mark, we're done. We have verified the identity. Now, we broke a couple of rules here that we normally don't like to break. We left the 1 there technically, but the cosine was added to the other side, and then the previous step was to multiply by sine squared both sides. So anyway, did we verify it? Yes, we obviously did, and it works. Let's go ahead and try number 2. Okay, number 2. So secant squared of x minus cosecant squared of x equals tan squared of x minus cotangent squared of x. We're going to leave the right-hand side as is. We don't want to touch that. But we can definitely change around secant and cosecant based on our Pythagorean identities. Now, that minus sign obviously is going to be super, super important in a minute. But let's go ahead and change our 2 advanced trig values here. Secant is tan squared of theta plus 1. I'm going to use x instead because that's what the problem had originally. So we're going to change secant squared of x to tan squared of x plus 1. Now, minus the cosecant, which we're not going to change just yet. I want to see this into completion. So we'll just rewrite the right-hand side with no changes. So now, again, we have tan squared x plus 1 in place of secant squared x. Now, we can change the cosecant as well because the Pythagorean identity is 1 plus cotangent of squared of theta. So tan squared of x plus 1 minus the quantity now of 1 plus cotan squared of x is going to equal tan squared of x minus cotan squared of x. Now, because it's a minus sign here, we have to be really careful about how we use PEMDAS and how we combine like terms. That negative sign is actually distributing to both of these things, right? So then we're going to have tan squared of x plus 1 minus cotangent squared of x. And that's going to equal our right-hand side as normally, right? So let's combine like terms. Where was that? Why did I put that there? That was weird. Okay, do we have space? We do. Okay, so we have 1 minus 1, which is 0, obviously. So then we have tan squared of x minus cotan squared of x. And obviously that's going to equal tan squared of x minus cotan squared of x, which was the original problem. Check mark, we're done. We have verified the identity. Moving forward. Number 3. Cosecant squared of x times cosine squared of x is going to equal cosecant squared of x minus 1. Go ahead and pause me and see if you can do this one on your own. I'll be right back. Okay, you're back. So obviously, if you got to this level, you're looking good because you verified the identity correctly. But what did we really do here? Well, we did a couple of crazy things first. Actually, they're not that crazy. I don't know why I said crazy. That's pretty stupid. Okay, so we had our original problem here. Oh, that was really hot. The lights here, that was more warm than I thought it was going to be. Okay, so with cosecant, we know that cosecant not only is 1 plus cotangent squared of theta, but it's also the inverse of sine. So we could have just did 1 over sine squared of x, is which we wanted to do. Now, would you have been totally wrong if you got 1 plus cotangent of squared x? No, not really. See, the beauty, or I guess the horror of this, is that there are multiple ways of doing this. You want to find the most efficient way, but sometimes, especially when you first start this process, you're not going to have the most efficient way available. You're just going to try to use whatever you see. And that's okay. You're going to get better at it through time. So we did 1 over sine squared x times the original part, cosine squared of x. Obviously, we left RHS the same. Now, we combined the terms here by multiplying, which gave us cosine squared of x over sine squared of x, and that's going to equal cosecant squared of x minus 1. Again, didn't change right-hand side at all. But cosine over sine is cotangent. So we replaced the fraction with cotangent squared of x, which equaled RHS. Now, that's not actually the identity. 1 plus cotangent is the identity. So really what we just did was we added 1 to both sides, which proves the identity true. Cotangent squared x plus 1 equals cosecant squared x. Done deal there. Last one we'll do. Okay, now with number 4, it's just about maybe an observation because there isn't any verification needed here because this isn't verifiable. So the one thing that we have to remember about even and odd identities is that the negative, if it's on the theta or x measurement, it's the same thing as if that exact function is -2. Now because we have a rational trigonometric function here, that negative can go a couple different places. So really what we're looking at is this. A reordering, not so much of a verification. So cosecant of x is going to equal sine squared x minus 1 over negative sine of x. Or we could take that negative away from the sine of x and actually put it in the front of this entire function, which makes that a little bit more challenging to solve when we do get to that. But when we talk about the even odd identities, there isn't much of verification done, especially with this function. All I want to do is be able to recognize that the negative that was next to the x could go in front of the denominator of that function sine or in front of the entire thing of sine. We would eventually distribute that minus sign to everything, making that a +1 long term, but it isn't super important on where that negative goes as long as you know it can go elsewhere. Let's finish up. Things to remember about this video. Number 1, formulas. They are super crucial when it comes to you having success with simplifying, verifying, and then obviously moving forward into other videos in the future, solving. Number 2, think of proving identities as a puzzle. The right-hand side is giving you the picture of the puzzle box or the completed puzzle. You're just trying to get to it. So every time we try these things, you might find a new shortcut, or you might find a better way or something that's more efficient to try it. Just make sure you're matching left-hand side to right-hand side. And then number 3, I just touched upon it a little bit. There's always another way. Sometimes those ways take you far, far down the rabbit hole, but other ways are way more efficient. And when you get more comfortable with these formulas, you'll be able to find that efficiency. See you next time.